In this video, we are going to go over section 7.3, maxima and minima. The goal of this section is to find the local max and local mean of a function of a several variable. This concept we have already went over in chapter 2 when we were dealing with the function with one variable. So the same concept will carry over with the function that has a multiple variable. So recall that to find the local extrema, what we did was we took the first derivative and then set it equal to 0 to find the critical point. And then we did the second order derivative, so second derivative, to find out where is local max and then local mean. So the critical point really means potential local mean, local max. That critical value could be local max or local mean or nothing. We call that saddle point. So we are going to take the first order partial derivative, set it equal to 0 to find the critical point. Take the second derivative, second partial order derivative to find out the function value a, b, c, plug it into the formula ac minus b squared to check and see which point is a local max. So case 1, ac minus b squared is a positive and a is a negative, then our critical point is a local max. Case 2, ac minus b squared is a positive and a is a positive, then we call it local mean. ac minus b squared less than 0, that's a saddle point. So anything negative will be a saddle point. If it's equal to exactly 0, the test fails. That means we have no idea if it's a max, min, or saddle point. So it doesn't tell you anything. So let's jump on the first question. So we have a function f of xy defined as 14x minus 9y plus 21. Find the first partial derivative, then explain using theorem 1 why f of x comma y has no local extremum. So let's start taking partial derivative. Partial derivative, we did that last chapter, last section. So first one, f of x comma y means I'm taking derivative respect to x. So x is my variable. So derivative of a 14, x will be 14. And then remaining term will be just 0 because it's a constant. F of y, x comma y, it's the same function, but this time I'm going to take respect to y. So this will be the variable that I am interested. First function, because it's a x, it will be a constant. 9y, derivative of 9y is negative 9. 21 is just a constant. So here we get a f of x equal to 14 and then f of y equal negative 9. Why is there no local mean max? Well, in order for local mean and local max to exist by theorem 1, we need to set each function equal to 0. And since the partial derivative respect to x and y cannot be ever equal to 0, because you get 14 and negative 9, then we don't even have to continue with the rest of the step. We can just say there is no local extremum. Okay? So I'll write a sentence here. Since the partial derivative with respect to x and y cannot equal 0, there is no local extremum. Okay. So let's take a look at the other two example where we do have a local extremum. Okay. So two more, and then we have two application problem. Number 2. So we have a function, find the local extremum. So that means I have to go through 4 cases. Let's start with taking the partial derivative respect to x and y to find the critical point. So I'm going to take f of x. So that means my x is the variable, y is a constant. So it will be 14x constant plus 3 constant. Okay. F of y, x comma y, I will erase completely so it doesn't get confused. And then I'm gonna highlight y. This is my variable and this is the variable. So this one is a constant, so it does disappear. This will be negative 10y, constant disappear, minus 4, constant disappear. So we are done with taking the derivative, first derivative. Now we are going to set these two functions equal to 0 to find the critical point and test the critical point later on. So let's set it equal to 0 and solve for our x and y value. Subtract 3, I have negative 3 equals 14x divided by 14. I have x is equal to negative 3 over 14. Similarly, add 4. I have 4 equals negative 10y divided by negative 10. Y is equal to reduced negative 2 over 5. So based on the above partial derivative, we do have a critical value point at negative 3 over 14, comma, negative 2 over 5 is a critical value. Okay. Now let's find A, B, C. And then plug it into the formula to check which one is a local mean. Or to check our critical point is either case 1, 2, 3, 4. Now, to find A, B, C, I need to take second partial derivative, f of xx, f of xy, and then f of yy. So, let's start with A, which is f of xx, a comma b, right here, a comma b, which is our critical value. This is A, this is B. So B is f of xy, A comma B. C is f of yy, A, B. So f of xx, so that means to find out the capital A, I'm going to be using this function here because I already took the partial derivative of x, right? And I'm going to just take the derivative respect to x again. So here, I'm going to have x is my variable, so I end up getting 14 and 3 disappears. B, same function x, so I'm still going to use this one, and then I'm taking derivative respect to y. None of the variable is a y, none of the term is a y, so it will be 0. Now for C, I'm going to be using f of yy, this function here. So I'm going to take respect to y again. So y is our variable. So this one disappears. So C ends up being just a constant, negative 10. So let's plug it in. I'm going to make this smaller so we have a space. So let's plug it in. AC minus B squared to check and see which case it follows. So A 14 times C negative 10 minus 0 squared, that will be negative 140. Since this is negative 140, it will be case 3. You have negative. So what does that mean? It's a saddle point. So it's neither local max or mean. So that's it. That's how we check and see if there's local extremum. Since the above value is negative, the function f has a saddle point at negative 3 over 14, comma, negative 2 over 5. Okay. All right, number 3, one more practice going through the 4 steps. Okay. First, let's take the partial derivative, first order partial derivative, set it equal to 0 to find the critical point. So here, f of x, x comma y, my x is the variable. So it will be this term and this term. So 2x squared, derivative of 2x squared will be 4x, constant disappear, 7, constant. F of y, x comma y, same function, but this time I'm going to erase so that I don't get confused, and then take respect to y. So first term is a constant, so disappear. 4y squared, derivative of 4y squared is 8y. Constant disappear, minus 3, constant disappear. Let's set these two equal to each other. Let's set these two equal to 0. So 0 is equal to 4x plus 7. 0 equals 8y minus 3. Minus 7. I have 4x equal negative 7. Divided by 4. X is equal to negative 7 over 4. Over here, we add 3. So I have y is equal to 3 over 8. So based on our first order partial derivative, negative 7 over 4, comma 3 over 8 is a critical value. Okay. And let me also resize this one here. So now let's continue. Right over here, we'll take the second order partial derivative to solve for a, b, and c, and then test the value. So a is defined as f of xx, a comma b, and then b is f of xy, a comma b, and then c is f of yy, a comma b. So this is the function that I'm looking at for this one here. So it's already, first derivative is fine. So second derivative respect to x of 4x plus 7, I'm going to end up having just 4. The 7 disappear. B is still same function, but respect to y. None of the variable is y, so I end up having b equals 0. C is the function that deals with this one here because it was first derivative was a y, so I'm looking at this one. And then let's take one more derivative respect to y. So I get c is equal to 8. 408. So ac minus b squared will be 4 times 8 minus 0 squared. So we end up having 32. So this time we get a positive. So it will be case either 1 or 2 because it's a positive. Is A negative or A positive? Well, A is 4, which is positive. So this will be case 2. So our critical value is actually a local minimum. So that's it. Case 2. So it's a case 2. So we will say the function has a minimum at the point -7/4, comma 3/8. Okay. All right. Last two problem, application problem. So let's take a look at number 6. A company produced 2 types of toy cars per day, X unit of type A, Y units of type B. If the revenue and cost equation for the day are in thousands of dollars, we have R function, the revenue, and then cost function. Determine how many of each type of toy should be produced per day to max profit. And what is the maximum profit? So we need to find out how many of each type. In other words, what is my X and then Y that will give you max profit? And then what is it? What is the actual profit value? So first, I do not have a profit function, so let's begin finding the profit function. We have done similar problem in the earlier section in 7.2. Here, we have this train problem, and then we have a revenue and cost. So the profit was found by subtracting the revenue minus the cost. So I'm going to do that same thing. So first, let's find out the cost function. Profit function. So P of xy will be R of xy minus C of xy. So it will be 25x plus 31y. I'm going to distribute this negative into all this, so because we are subtracting, so it will end up being, so we save time writing the numbers, negative 2x squared plus 5xy minus 4y squared minus, so negative, positive, minus 9y minus 7, because all the negative is distributed. Let's combine like terms. So I have x squared term alone, y squared term alone. I have 25x with the 5x that I can add together. I have the y term that I can add together. And then this will be alone. And this will be alone. So combining P of x comma y, negative 2x squared, and then I have 5 plus 25 makes it 30x, and then we have plus 5xy, and then 31 take away 9 will give me so 31y take away 9, I get 22, positive 22y minus 7. Minus, last one, 4y squared. Let me just double check. Yep, that looks good. Because we want a max profit, we want to find out, we want this one here, this case. So we will take the partial derivative and then set it equal to each other, set it equal to 0. For this one, I'm going to take respect to x. So here, I'm going to underline it, this one, this, and then rest of them is just a constant. So I have negative 4x plus 30. Now x is my variable, so 5y is a constant, so 5y, and remaining one will be just zeros. P of y, x comma y, so that will be taking respect to y function, so there's my y term, there's my y term, there's my y term. So the first two term is constant. 5y derivative of y is 1, so 5x plus 22, and then minus 8y. Okay, now let's set it equal to 0 to solve x and y to find the critical point. So this one, I'm going to add 4x minus 5y, add 4x minus 5y. We have to do the process of elimination in algebra. Two unknowns, two equation. Go to 30. Here, I'm going to subtract 5x, add 8y. Subtract 5x, add 8y. So negative 5x plus 8y equal to 0. Now let's set these line up. So using elimination. Oops, I keep saying equal to 0, but it should be equal to 22. Depending on which variable you want to eliminate, I'll just eliminate x. So that means I need to multiply the top by 5 and then here by positive 4. So I'm going to end up getting, so first one I have 5 gets distributed to all of them. So I have 20x minus 25y equal to 150. Here I'm going to have negative 20x plus 32y equal to 22 times 4, which is 88. Adding these, x term disappear. And then we have 32, take away 25, 7y. And then 150 plus 88, I have 238. And I'm going to divide it by 7. So I end up having y is equal to 34. Now let's plug it in either equation. I'll just plug it into here to solve for x. So negative 5x plus 8 times y, 34, equal 22. So negative 5x plus 8 times 34 will be 272 equal 22. Subtract 272. Negative 5x is equal to negative 250 divided by negative 5. I end up having x is equal to positive 50. So this is my critical value. So let me add a page. So from this, we get 50, 34 is the critical point. Now we are going to solve A, B, and C and make sure that this critical point is the case 1 because we want to max profit. Okay, so we want this to be case 1. Okay, let's check. So A is defined as P of xxa comma b. B is P of xy, a comma b, and then C is defined as P of yy, a comma b. Now let me bring my first order function. So this one was our first order function. And then this one here is my second one. So let me just do a little bit of rearrangement. So this is p of x function and this is p of y function. So now let's take the first one, p of xx. So I'm going to be using this one and then take derivative respect to x again. So it will be only this term, so negative 4. Second one, same thing. I'm still going to use the purple one, but this time I'm going to take respect to y. So this term. So I have b is equal to 5. And then c is this function here, p of y, respect to y. So this one. So I have negative 8. So let's check ac minus b squared will be negative 4 times negative 8 minus 5 squared. So it will be 32 minus 25. So 32 take away 25 will be positive 7. So that's good. We got the first case. We got positive. Is a negative? Yes, a is negative. So it is case 1. So the above value is our maximum. So that means our critical point is local max. So our critical point 50, 34 is our local max. Uh, 50, 34. So that means, remember this is x and this is y. So we need to have type A, how many? 50, and then type B toy, 34. You should produce 50 of type A toy cars, and 34 type B toy cars to maximize your profit. That will give you maximum profit. Now the second part is, what is the maximum profit? So I'm going to be plug it into our profit function with our unit 50, 34. Okay. So that will be the last part. Copy. Let's erase. Okay. This was our profit function, and we are going to plug it in with 50, 34. So piece of 50, 34, negative 2 times 50 squared, plus 30 times 50, plus 5 times 50 times 34, plus 22y will be 34, minus 7 minus 4 times 34 squared. Okay, so my final answer, plug it in everything into a calculator, I get 1117, $1,117. Okay. All right, let's move on to our last application problem. Number 7, a rectangular box with no top and 2 parallel partitions. So we have a box with no top, but we are partitioning 2 parts. must hold a volume of 125 cubic inches. Find the dimension, so that means dimension of this box. That will require least amount of material. In other words, least means we want to minimize the value. So I'm going to kind of draw the figures so that I can see exactly what's going on. So we have a rectangular box with open top. And let's label X, Y, Z. And then not only that, I am partitioning this part with a two parallel partition. So kind of like we have one partition and then the second partition. Not really good with the drawing here. So kind of like divider. So there's two parallel, this will be the two parallel partitions. So we want to find the dimension XYZ, right? So XYZ, that will give you minimum materials. So let's come up with the function of, I'm just gonna call it M. What are the things that creates this box, right? So we have kind of like the bottom that we need to build. And we have, I'm going to label this here, kind of like the side. But we have 1, 2, 3, 4 because I'm making the partition. So I'm going to say 4 sides. And we have kind of like front, which is this part here, front of the box and back of the box, right? So plus front and then back. And another thing is we know this volume, which is X comma Y comma Z is equal to 125 cubic inches. So that's what we know. So let's write it out. The bottom is this figure, this will be X times Y, right? So this will be X times Y. The 4 sides are Y comma Z, Y times Z. But there are 4 of them. So 4 times YZ. And then front is made up of X times Z. But we have also the back, another X times Z. So combining, I can combine these two. I have M, the material, XY plus 4YZ plus 2XZ. Okay. All right. Now we have 3 variable and that gets a little bit too much. So let's reduce. We are gonna use this function here to do some substitution. So we are dealing with 2 variables because we are only having these 2 variable function here, Z. In order to use these cases, I need to write this as a X and Y. So I'm going to substitute so that Z disappear. So first case, what you can do is you have this XYZ equal to 125 and take a look at this XY. This first term is fine because of X and Y, but in here you have a Y and Z. So if I divide it by X, I have YZ is equal to 125X. And that's what I'm going to substitute here, YZ with here. Now, same thing here. I don't want the Z here, so another thing you can do is with the volume, I can divide it by Y. Then you have XZ is equal to 125Y. And I'm going to do that substitution so that we are dealing with just the 2 variable. So my M is defined only variable XY. And then YZ is 125 over X. And then 2 times XZ will be 125 over Y. Okay. So let's keep going. So M of XY plus 500 over X plus 250 over y. Okay. So that's good. We have two variables. So now we have an equation. Let's do the same thing. M of x, x comma y. If I take the partial derivative respect to x, first one I'm going to have a y. Second one, if you want to, let's even make it more friendly, derivative friendly. So I'm taking respect to x, so this term and this term. So I have minus 500x to the negative 2. In other words, we have y is equal to negative 500 over x squared. Now, taking the partial derivative respect to y, first order partial derivative respect to y, I'm going to have y term and then y term, this one. So same thing here. First one, y is the variable, x is the constant, so x. Second term disappear. Last term minus 250 y to the negative 2. So my function will look like x minus 250 over y squared. I'm gonna set these function equal to 0. To find the critical point. So if I set this one equal to 0, and then this one equal to 0, let me let's see, what can I do here? I'm going to do the substitution. I'm going to solve for x here, so add this and substitute my x into the other function. So 250 over y squared equals x. Over here, I can also have add 500 over x squared, add 500 over x squared. So I have 500 over x squared equal y. Now, I can multiply x squared. Actually, yeah, I will multiply x squared because I don't like fraction. So I have 500 equals x squared times y. And this is part where I'm going to do the substitution. I'm going to substitute the x with 250 over y squared. So I have 500 equal to 250 over y squared times y. So solving, I can, oh, don't forget the square. So 250 squared is 62500 over y to the 4th times y. I'm going to cancel one of the y, so that will be 500 is equal to 625,000 over y cubed. And let's do the proportion. So I have 500 y cubed is equal to 625,000. Let's keep going and solve for y. We're almost done. So y cubed is equal to, I get 25 cube rooted, 125, I'm sorry. Cube rooted y is equal to 5. So that means x will be 250 over 25. X will be equal to 10. So 10 comma 5 is our critical value. Okay. So that is step 1 and 2. We found the critical value. Now let's take the second order partial derivative to find out A, B, and C. And this time, this particular example, this problem, we want case 2 because we want to minimize the cost. So let's set up. So I'm going to have A is defined as m of xx a comma b, and I'm going to actually put it over here. And then B is defined as m of xy ab, and then C is defined as m of yy ab. And I'm going to copy these two. And then also note that this is our critical value. Okay. So let's start with A, m of xx. I'm going to be using this one and then take derivative respect to x again. So this part disappears. And then this is the only thing. So I end up having, you can also think of it as 500 x to the negative 2. So A is 500. So let me write it out. I like to write it out. Let's do a little bit of a work here. So m of xy can be rewritten as negative 500 x to the negative 2. And then this can be rewritten as x minus 250 y to the negative 2. So I'm going to have this term disappears because it's y. This one, negative with this negative 2 will make a positive 2. So I'm going to have a positive 2 times 500 x to the negative 3. So in other words, A is 1000 over x cubed. Okay. And then I know that x is 10 because remember this is at a comma b, so if it's not a constant we have to plug it in, so that is 10 comma 5. So x, so 1000 over 10 cubed, so this will be equal to 1. So a will be 1. A, B, C has to be a number because when we are checking these, we want to check and see if it's a positive or negative, so it has to be a number. So make sure if you don't get any of the constant, plug it in with our critical points A comma B. B, let's find out. Still same one, but I'm taking derivative of respect to y, so the only surviving term is y, so derivative of that will be 1. C is this function here. And then I'm going to take respect to y. So in other words, this is the term that I am taking the derivative. So negative 250 and then negative 2 comes down and then subtract 1, negative 3. So I end up having 500 over y cubed. So again, it's not a constant, so we plug it in, 10 comma 5. Y is 5, so 500 over 5 cubed. So I get it equal to 4. So C is equal to 4. So let's check AC minus B squared. So that is 1 times C, 4, minus 1 squared. So I have 4 minus 1 equal to 3, which is positive. And then we have A is equal to 1, which is also positive. So we get positive and positive, and that's good because we want positive and positive. So indeed, our critical point is local minimum. So this is case 2, confirm. So over here, I'm going to have the function, so local mean. So the function has a minimum point 10, 5, which means, therefore, remember x and y, x was your length, y was a height, but we need to solve for z because we want the whole dimension, so we'll use this function to find out. So x will be the length, x will be 10, the width is 5, and then the height, which is z, and then z can be solved right over here. So I have xyz equals 125. So let's plug it in. X equal 10, y equal 5, z 125. So 50z is equal to 125. Let's divide it by 50. Z is equal to 125 divided by 50. I get 2.5 inches. Okay, and that's it. That will give you our minimum material. And it's asking you to find the dimensions, so we are done. All right, that's it for chapter 7.